Hello, welcome to the Edsim++ instruction video called Building Custom Objects. My name is Nico Punt and I will show you today how you can extend the Edsim++ PKPD library by creating new objects. And I will show you this on a question I received from a user recently, and he asked me whether it is possible to control the elimination over time. And I added a question myself to this question, and that question is, can I control the volume of distribution over time? And there are a number of solutions for this problem. The first possibility is that you use the allometric scaling feature of Edsim++ to scale a parameter to some patient variable. For instance, you could scale the volume of distribution to body weight, and you can typically also scale the elimination, the clearance to, for instance, the patient body surface area. With respect to elimination, you could also add a hemodialysis object to manipulate the elimination. But a third option, which I'm going to show you today, is to create a new PKPD object which can do this for you.
So now we will first start by creating a new elimination object called TMyElimination, in which we add the possibility to control the elimination over time. And there are some distinct steps involved here. What we'll do is we will use the existing TElimination object as a base. And we will derive the new object from this, and this is called inheritance. Then we define a new variable called fcore. Core stands for correction, and we define this as a so-called tint variable, which means it is an interpolatable variable. Then we define the equations that we require here, and then we have to rebuild the library. And when we did that, we can start testing this new object. So let's have a look first how the output objects are organized, and we can do that by having a look at the PKPD library documentation. You can view that by clicking under Help Library. And so here you see the inheritance tree for the output objects. And so all objects are derived from an object called boutput. It's an abstract class, so you cannot create objects from it, and but it's used to group all output objects. And derived from this is a object called TOutput, and TOutput only defines the differential equations to take into account a certain elimination rate. And the actual elimination rate is calculated in the objects that are derived from TOutput, like for instance in TElimination. Okay, so I close this. So how can we look at the source code of this TElimination? What we can do is, if you drag an elimination object on the desktop, and if you double click and look at the object tab, you see here this little button called code. Now if I click here, you see the source code of this object. And so what you can see is that all these objects require a certain library, mediware.edsim.modelib, and all the code must be in a particular namespace called mediware.edsim.modobject. So those are the things you have to get right from the start. And then you see here some compiler directives. First there is a description compiler attribute which describes the class, and there's also a special attribute called source and target, where you can specify what kind of objects can be the source for this object, and what kind of objects can be the target for this object. So in this way you can control how this object can be connected to other objects. Okay, in this statement here, we say that the TElimination object is derived from a TOutput base class. And on top of that we define new variables in this class, TElimination class. First we have a mode variable, which is a so-called option constant. And then we have two other symbols. These are parameters. One is the rate constant, the elimination rate constant, and the other is the clearance. And you can see if you make a new instance of the clearance, you can specify what quantity it should be and what its default value should be. And the same for clearance. So you see that the clearance has a quantity of flow, while the elimination rate constant has a quantity of fractional rate. So that's in fact 1 per hour. Okay, here you see the constructor of this object, and in the constructor we define the option values. So we have two options, one called rate, which is associated with a value of 0, and one called clearance, which is associated with a value of 1. The function final is called by the Edsim++ framework, and it's called after all connections have been made. So it's the last initialization possibility you have. And what we do here is we have a look at the value of mode. So if mode is 0, then you see that you have your primary parameter will be the elimination rate constant. So this parameter can be fitted. And of course, if k can be fitted, the clearance cannot be fitted, and vice versa. So, and why is this? Well, you can see that in this next procedure called calc norm. And calc norm is a function called by the Edsim++ framework to calculate all your equations that have nothing to do with differential equations. So everything except differential equations. And again, here we look at the mode value, and if the mode is 0, so it's the rate mode, then we calculate the clearance based on the value of the rate constant. So here clearance is rate times volume. Or if we are dealing with a clearance mode, so the value is not equal to 0, then we calculate the rate constant as being the clearance divided by the volume. So whichever route we take, we have here a known k value, rate value, and then we can calculate the elimination rate as this rate value times the amount which is still in the source compartment. AX is the amount in the source compartment. Now, you see here that this TElimination is derived from a TOutput, and but you cannot make objects of TOutput. So I can not look at the source code as I did for the TElimination by clicking on this button, but I can do it in a different way. I can open explicitly a source file, a C# source file, and I have to look down in the folder objects, outputs, and I look in TOutput, and I open it, and I have here, oh, I made a mistake. I have to do it like this: open object, and I can select TOutput. Yes, now I did it the correct way. So here you see the definition of TOutput, which derives from this grouping class called bOutput. So here some addition symbols are defined. So everything denoted with an X means source. So this is the volume in the source compartment, and we have to state the name of the symbol in the source compartment. This is simply V for volume, and we have to say we are dealing with the source. And here is the amount in the source compartment. We also define a new amount variable called A, which is simply the total amount eliminated. So it's accumulated, elimination over time. And here the variable R is the elimination rate. So, and here the differential equations for this output object are defined. So this function collectDiff is called by the Edsim framework for calculating differential equations. And here you see that the not the value of these amount variables in the source compartment and in the current object are updated, but the delta property. And this delta property is then used by the integrator to integrate these differential variables. So it's quite simple. So a negative value of R, the elimination, the transport rate, is applied to this source amount, and a positive R value is applied to this target, or in this current compartment of the current output object. Please note the plus is operator here, because there are more objects that can contribute to this delta value. So there could be several outputs attached or inputs attached, and they all have their own contribution to this delta value. So you must say plus is. Okay, now let's close this again. So now we will create our own object. So I say new object. And you see here that in the object tab there is created a template for me. So these things I mentioned earlier already, that you have to use this library and have to use this namespace. It's already in. And I can add a description here as well. So what I will do is I say, okay, I just leave the name TMyCompartment, and I say, okay, no, I will change the name to TMyElimination, because that's what we are working on right now. And we derive this from TElimination. We don't need this init function. Init is called is an initialization called prior to linking the objects. And as I told you, final is called by the framework after the objects have been connected. We only require this collectNorm function. We don't use the collectDiff function right here. Okay. So what we're going to do now here is we define a new interpolatable variable called fCorrection. So we do that like this. So an interpolatable variable is called tint variable. You see here that the built-in C# editor has IntelliSense enabled. So what I can do is new T. Here it is, tint variable. And I have to specify the quantity. We use actually a different overload method. So we have to specify the unit first. So we say, okay, we know that there's no quantity associated with this variable, and we simply use the default unit, which is in fact no unit in this case. And the default value will be 1. So now we defined our new variable. And now we have to define our equation. So remember that we are inheriting from the TMyElimination object, which already has definitions for the normal equation calculations and the differential equations. So we add our new functionality. So what we do first is we call the collect norm function of the base class, like this. And after that is done, we will apply our correction. So we know that we have to adjust this R value, the transport rate. So R dot value is R dot value times, correct that, times the F core dot value. Okay, so this is in fact this is our new object. As simple as that, and that's only possible through this mechanism called inheritance. Before I will build this object, I will make a typo. I will make a mistake. Let's say I forget the E here, and if I now build this object, I have to say where I want to store it. No, it's an output, and it's called TMyElimination. And I save it. And then it says the value is not defined. So I must add the E and rebuild it again. Now it's okay. So I must now rebuild the library. And it says I must restart Edsim in order to use this new object in the library. Okay. So now we must test our new object if it's working okay. So what I'm going to do is I add here a compartment, and I attach an elimination, an output to it. And now let's see if our new object is in the list. And there it is, TMyElimination, my new object. I select it, I double click it, and look here, I have a new variable called fcore with a default value of 1. And so what I can do now is I can set the values. So I want to observe this variable, and I'm going to set some observations here. So I will select here fcore, and what I will do is I will add a series of observations. So well, initially it will be 1, and after 5 hours it's still 1, and then we start changing it. For instance, at 10 hours it's 0.8, at 15 hours it's 15 hours it's 1.2, and then after 20 hours it's 1 again. So now if I simulate this, you see here this correction, the fcore value, starting at 1, and at 5 hours going to 0.8, then going up again at 15 hours to 1.2, and then at 20 hours going back again to 1. So this here you see how we can control this correction factor. You see that the values between the observations are interpolated. If you want to, you can switch that off. So if you go here to variables and you say here no int, and I simulate again, so you simply it get the staircase. So there's no interpolation, it just changes in the moment you have this observation. So, but I will switch it on again, like this. So now the question is, of course, but does it really affect my elimination? Because we're now just only looking at the correction factor. So in order to investigate that, we create a model in which we start an infusion into this compartment. We say this is an infusion, and I always, if I go to the schedule, I always have this little trick that I take an infusion duration equal to the interval time, and then I will simply say, okay, this is the number of hours I want to have this continuous infusion. I will remove my observations from this the correction value, because I will change that later on. I first want to have a look what's happening without this correction. So I simulate this, so we get this nice continuous infusion on steady state. So, and this is always my favorite technique to demonstrate things, because once we are in a steady state, we can do some interventions and see the effects of this. So let's start fiddling around with this correction factor at, say, 100 hours. So I go back, I go to my new elimination objects, and I select here the correction factor. So at time 0 it's 1, at 100 hours it's still 1, and then we start changing things. Or 100 hours, or maybe somewhat later. 100 hours is perfectly. So let's say we go to 0.8 at 120, and to 0.5 after 140, 100, and at time 160 we go up to 1.2, and at 170 we go up to 1.5. Purely hypothetical, of course, but it's just to demonstrate the effect. So I will simulate this, and then you see directly the effect on the steady state concentration. So at this point we make the elimination slower, and you see that the concentrations go up. But before it can reach steady state, we're already doing the reverse. We make the elimination faster, and the concentration will go down. And what you see here are the observations for this correction factor. So if I go back here to the variables, what I can do is I can show this correction factor on the opposite axis, so that we have a better view. So simulate this again. We have this nice view here. So infusion going to steady state. At this moment we lower the elimination rate by our predefined factor, and we see concentrations going up. And the moment we do the reverse, we increase the elimination rate, we see concentrations going down. So this is a nice proof that this is working. So now we move on to the second question, and that was, can we create a new object in which we can control the volume of distribution in very much the same way as we did control the elimination in a output object. So we're going to create a new object called TMyCompartment, and it involves the same steps as we saw earlier. So we have to derive a new object from TCompartment. We have to define a correction factor. Then we define the equations. We rebuild the library. We're going to test the object. Okay. So, but first let's have a look at the at how compartments are organized in the library. So I select library again, and here you see an overview of the inheritance tree of compartments. So the most important one is, of course, our base compartment, T compartment, which is usually used as the central compartment. And derived from this is the sink compartment and peripheral compartments. So let's have a look at the code of a T compartment object. So I will simply add a compartment to the desk, double click it, look at the object tab, and click on code. So here we see again how this compartment is defined. in very much the same way as a elimination object. So most importantly, the compartment defines amount, which is a differential variable, and it defines volume of distribution, concentration, C, and the free concentration, Cu. And so let's focus now here on the normal equations. Here you see that the concentration is calculated as the amount divided by volume, and the free concentration is calculated as the fraction amount times the concentration. So it's very simple. There are no differential equations involved because these are contained in objects that connect to a compartment. Okay, now let's build our new compartment. So I say new file, new object, and I am presented again with this template. Okay, I'm only going to use this calc norm function, so I can delete the other ones. So TMyCompartment is okay, and I will derive this from a T compartment. I will define this correction factor again. So it's again so this is our correction variable. Oh, I made a typo here. Should be T quantity. And now I will enter the equations. So again, we of course have to call the equations, the normal equation, in the base object, in the compartment object. But the order in which we apply our correction and the calling of the base equations is very important. So remember that in the base object, the concentration was calculated, and that was calculated using the volume of distribution. So we first have to apply a correction to the volume of distribution. So we do that like this. And then we have to call the base equation like this. Okay. So what you see is we multiply the initial value, V_ini, of the volume of distribution with this current correction value to obtain the actual volume of distribution. And then we call the normal equations in the base class so that the concentration is calculated in the proper way. So this is in fact already all what we need. So I can try to build the model. I have to say where to store it. Okay, this is a compartment. I call it TMyCompartment. And I will save it. And it's compiled. And there were no errors in it, so I can rebuild the library. And of course, I have to restart Edsim again in order to use the new object. So now going to test our new T compartment object. So I add here a compartment, and let's see, yes, there it is, TMyCompartment, the new compartment type I created. And if I double click this, I see here this correction factor, which I added to this compartment type. So I switch it on to observe it, and I will enter a number of observations. So let's say at time is 0, the correction factor is 1, at 5 it's 1, then at 10 it's 0.8, at 15 it's 1.2, and at 20 it's 1 again. Now if I simulate this, we get this nice graph of our correction factor. But how does it affect the volume of distribution? Well, we can derive that indirectly by giving an amount into this compartment. So if I go to variables, I say, okay, the amount is 2 milligrams. So the initial concentration will be 2 milligrams per liter, because the concentration is 1. So if I simulate this, you see here the correction factor and here the concentration. So if the factor is below 1, it is going down, the concentration goes up, and vice versa. There's another way, a more direct way, that we would like to show the volume itself in this graph. But that's a problem, because volume is a parameter, and you cannot show parameters in graphs. But there is a way to do it, and that's as follows. You can add a monitor tool. So I add a tool, I change it to monitor, I connect it to the compartment, and now I have to specify which symbol I want to observe. So I go to the external list, and I change the default value of C for concentration to V of volume. And I go to here to variables, and I say, okay, I want to observe this. Here I will switch this off. I don't want to observe concentration again. So if I simulate this, you see that the volume, which is exactly 1, now follows the correction factor. So I can make it a little bit different if I now change the volume, for instance here. So I will remove the amount, and I will change the volume to 2. So if I simulate again, then you see here the volume, which was 2. So if I make the correction factor lower, the volume goes down. If I make it higher, the volume goes up. Now what happens if we have a peripheral compartment? So let me add one. I make a connection. I want to monitor the volume in this peripheral compartment. So what I do is I duplicate this monitor, connect it like this. Let me check if I monitor the correct variable. Yes, V, I monitor V here. Let me see if it's observed. Yes, it's also observed. And let me see what is the parameters. Well, we are using the rate mode. If I look at the option, we're using the rate mode. So, and here are the parameters. And what I will do is I will change this parameter, the ingoing rate constant. I will make it twice as high. Now, if I do a simulation again, then I see only 2 curves. That's because, let me see. Yes, the correction factor goes right over it. So what I will do is I will remove the observation of the correction factor right there, and right there. No, of the correction factor. This is not the correction factor. This is the correction factor, and it's not in there. Okay. So what I see here is the volume of distribution in the central compartment, which I initially set to 2. And this is the volume of distribution in the peripheral compartment. And of course the volume of distribution in the peripheral compartment is determined by these parameter values, because we are using the rate mode of the peripheral compartment. So if I change the parameters here, let's say I make this 0.15, and simulate again, you see this change as well. So if I get closer like this, then those values get closer to each other. But what you see is that the volume in this peripheral compartment is actually following the volume in the central compartment. So, but what if we want to control the volume in the peripheral compartment independently from the volume of the central compartment? Now, if I change the mode to the clearance mode, then you see that the compartment has its own volume of distribution. Its latest calculated value was 1.82, but let's say I will say it's 1.5. And if I now simulate this, you see that this value remains unchanged. And only the volume of the central compartment is changing. So, and we cannot control this volume because this compartment has no correction factor defined for it. So what we could do is we could also make a special object that derives from the peripheral compartment. But there's another way to do it, and I will show you that. The alternative is to use two compartments, two MyCompartments objects, and then implement distribution using a transfer object. So I select here distribution. I connect them. Okay. I will add the monitor again to monitor the volume. Okay. So what I can do now is here in this compartment, I will observe this correction factor and I will enter observations. So I will say, okay, at time is 0, factor is 1, at 5 it's still 1, at 10 it's 0.8, at 15 it's 1.2, and at 20 it's 1 again. So right here is the correction factor. And the same sequence we use in the peripheral compartment, only we will change this. This will be 1.2 and this will be 0.8. Also like this. Okay. Now make sure that this the correction factor is observed. Other variables are not observed. Like this. Okay, no, I will not observe the correction factor. I will simply observe only the volume, which is exposed here as this variable. Okay. And so if I simulate this, okay, so let me change here the parameter to 0.2. Now if I simulate this, you see here the volume of distribution, and it's not exactly what we expect. It seems that the peripheral volume of distribution is still following the central volume of distribution. That's just because we have to select here a different mode now. We have to select under options the clearance mode, so that this compartment truly has its own volume of distribution. So I will set that of distribution that we set to let's say initially to 2. This volume of distribution is initially set to 1. So, and if we now do a simulation, Now we get what we expected, because the peripheral volume is increasing and then decreasing, while the central volume is decreasing and then increasing. And that's exactly in accordance with the observations we set right here for the correction factor of the central compartment and the correction factor of the peripheral compartment, where we reverse those two numbers. So what I'm trying to do now is do a real simulation with a concentration, and then see how the change in volume in the central compartment and change in volume in the peripheral compartment affects the concentration on steady state. So I will clean up the model a little bit, so I will throw away these correction factors for the peripheral and for the central compartment. Okay, let me move the model a little bit. Now I will add an infusion. This. And let's look at the schedule. So I'll make it duration of 1 hour, interval 1 hour, and then we'll take a very long time, 400 hours. I will add an elimination. Now, what is very important now is, because we are fiddling with those volumes of distribution, is that we select the correct mode, and that must be the clearance mode. If you select rate mode, then you get completely incorrect results. So there's really a special case here. So you have to use the clearance mode, just like with the distribution object. Okay, now let's see what kind of concentrations we reach now. So this is the concentration in the central compartment, and here the concentration in the peripheral compartment. And well, I could speed it a little bit up by making the distribution a bit faster here. So I will make it 0.2 distribution clearance, and then we have steady state here already. Let's say at 200. I will switch on the grid lines, so we get a clear view what's going on. Very nice. Okay, now here the volume of distribution is, let me see, 4, and here the volume of distribution is 2. Okay, and what I will do now is I first will change the volume of distribution of the peripheral compartment. So I go here to observations, and I enter a schedule for, yes, like this. I say, for instance, at time is 0, it's 1. At 100 or at 200, it's 1. But then very quickly we change it to 2. So we increase the volume of distribution of this peripheral compartment very quickly by a factor 2. And let's see what happens. So here you see, so the red line, you see very quickly the volume is increased, and then you see some redistribution from the central compartment to the peripheral compartment, but in the end you get the same steady state concentrations again. Now, if I do the same with the central compartment, so I remove it here, and I move to the central, I do the same thing with the central compartment. If I simulate this, then you see that the concentration of in the central compartment drops very quickly, and in the concentration in the peripheral compartment lags somewhat behind, because there is a redistribution to the peripheral compartment. Then it picks up again, and in the end you will reach the same steady state concentration. So it's easy to explain this result if you look at the equation for the steady state concentration. The concentration at steady state is defined as being the input rate
or in this case the infusion rate, divided by the clearance. And if you look at the units, you get the correct unit. So it's milligram per hours divided by liter per hours, and the result is milligrams per liter. So, but nowhere in this equation is the volume of distribution. So so you can have temporarily a change in concentration, but if the system moves to steady state again, it will be exactly the same steady state as we have shown here in the results. Only a temporary change, but then going back to the same steady state value again. Now let me clean this model. Well, these two models we now created, we call them TMyElimination and TMyCompartment. They are in fact already part of the PKPD library, and their names are, if I look at the compartments, control volume, and for the elimination, here elimination, it's called control elimination. So these are the objects which are in the PKPD library, which has exactly the functionality we have just created. So this concludes the video on building custom objects.